Math 1314, Tyler Junior College, Section 5.2, 3x3 Systems of Linear Equations. Application, ticket sales. In the previous series of videos, we did an example of ticket sales that set up a 2x2 system that we solved. This is similar to it. But the catch is, and this is a good bit of information to know for those of you going into physics, engineering, or upper level mathematics. If you need to find a certain number of values, you need the same number of equations. For example, if you want to know 3 values, you need 3 equations relating them. If you want to know 4 values, you need 4 equations relating them. If you want to know 10 values, you need 10 equations relating them. There's a course called Linear Algebra that gets much more in-depth discussion about the relationship between number of equations versus number of variables and the number of possible solutions you could have. But in general, to solve for a certain number of variables, you need the same number of equations relating them. Same number of independent equations, but let's not split hairs right now. At a recent show, 400 tickets were sold. The prices were $8, $10, and $12. The total revenue from ticket sales was $3,700. Let me stop here for a second. The question is going to be find the number of each type of ticket. If we stopped here, we would have two relationships between the tickets. Number one, the total was 400. Number two, the total revenue was 3,700. I can only make 2 equations from that, but I have 3 variables, which means I need 1 more equation. The total number of $8 and $10 tickets was 7 times the number of $12 tickets. There's my 3rd equation. Find the number of each type of ticket. This isn't nearly as hard as it seems. First, we need to represent each value that we want to know with a variable. We want to know the number of each type of ticket, and since there are 3 types of tickets, let's have an X, a Y, and a Z. X will be the number of $8 tickets. Y would be the number of $10 tickets. Well, it's going to be because that's what we're defining it as. And Z will define as the number of $12 tickets. The names of the variables are completely arbitrary as long as they're well defined. So what equations can we write? Well, the first one's easy. There were 400 tickets, which means the number of $8 tickets plus the number of $10 tickets plus the number of $12 tickets totals 400. Pretty easy. But what about the statement that the total revenue was $3,700? Well, now we need to add dollar amounts. How can we do that? However many $8 tickets we sold, if we multiply by 8, that tells us how much money we brought in. For example, if we sold 10 $8 tickets, 8 times 10 is $80. So in general, the revenue brought in from selling X of the $8 tickets is 8 times X. Similarly, the revenue brought in by selling Y $10 tickets is 10 times Y. And for the $12 tickets, 12 times Z. That total is $3,700. We've used this one. We've used this one, now we got to use this one. I'll admit, this 3rd condition is somewhat artificial. It's not wrong, it's just that who sells tickets and goes, oh look, the number of these tickets was 7 times the number of that. The total number of $8 and $10 tickets. So these tickets and these tickets combined, that's X plus Y, was equal sign 7 times the number of $12 tickets. Well, the number of $12 tickets was Z, so 7 times Z. And now we have our 3x3 system. I'm going to erase the board and move the system up so that we can have room to solve it. But half the battle is won. We've got our equations. Just remember that X is $8 tickets, Y is $10 tickets, and Z is $12 tickets. In addition to moving this up here, one of these equations needs to be rearranged in the proper form. I didn't mention it in this series of videos, but I really emphasized it in the previous series. When you're solving a system of equations, especially by addition, you should line up everything. X's, Y's, Z's, constants, and equal signs. This third equation needs the Z moved over. First equation, x plus y plus z is equal to 400. Second equation, 8x plus 10y plus 12z equals 3,700. I think I've said this before, but in case I haven't, when I write my z's, I put a line through them so you know it's not a 2. That's a 2, that's a z. Third equation, if we put it in the standard form, x plus y minus 7z is equal to 0. All right, let's attack. Equations 1, 2, and 3 for reference. Our first move, well, our next move, is to reduce this to a 2 by 2 system. So we need to pick a variable to eliminate and eliminate it twice. There's no wrong choice here. It's whatever's going to be easiest for you. I'm going to eliminate the z. Why? Well, I can eliminate any of them for the same reason, but this z has a 1 in front of it, and I can make that coefficient anything I want. So let's start by focusing on equations 1 and 2 with the goal of eliminating z. To make that happen, I would want a negative 12 in front of this z. So as a consequence, I'm going to multiply negative 12 times the first equation. And I'm going to leave the second equation alone. Negative 12 times the first equation is negative 12x minus 12y minus 12z equals negative 4,800. And the second equation as is, 8x plus 10y plus 12z equals 3,700. And if we combine them, we get negative 4x minus 2y, z's cancel, equals negative 1,100. There's our first equation in our 2 by 2 system. But we need to get a second equation by picking a different pair but eliminating the same variable. I'm going to use equation 1 again, but let's use equation 3 as well. Z, negative 7z. If I had a 7 in front of the first z, I would set up an opposite pair. I can get a 7 in front of the first z by multiplying the first equation by 7. 7 times the first equation will give us 7x plus 7y plus 7z is equal to 2,800. The third equation as is, x plus y minus 7z equals 0. This is easy to combine. 7x and x is 8x. 7y plus y is plus 8y. The z's cancel. 2,800 plus 0 is 2,800. We have our second equation with two variables. Let's take our new fourth equation and new fifth equation and make a 2 by 2 system. Negative 4x minus 2y equals negative 1,100. 8x plus 8y equals 2,800. Now let's set up an elimination. I'm going to show you a trick. I could play the same games I played before. Pick one of these and make it set up opposite pairs. If I double the first equation, the x's would cancel. If I multiplied the first equation by 4, the y's would cancel. But do you notice anything about all these numbers? They're all kind of even. I'm going to do something a little unconventional just to show you that you have options. But if what I show you makes you go, wait, I understood it up until then you do it the way I showed you the first time, which is to pick a pair, multiply to make a match. I'm going to make a match. I'm just going to multiply by something a little unconventional. I'm going to multiply the first equation by 1/2 to turn this into a negative y, and I'm going to multiply the second equation by 1/8 to turn this into a positive y. You just got to make a match. Nobody said the numbers had to get larger. Normally I wouldn't recommend doing this, but I just scanned every equation, every coefficient in the first equation can be cut in half cleanly, and it may not be obvious, but every coefficient in the second equation can be reduced by 1/8. If I take half of the first equation, I'll get negative 2x minus y equals negative 550. And if I take 1/8 of the second equation, I get x plus y And here's a trick for dividing something by 8. You cut it in half again, and then cut it in half again. Think about it. Half of this is 1400, half of that is 700, half one more time is 350. Don't believe me? Get out your favorite calculator and divide 2800 by 8, and it will tell you 350. It was an unconventional way to set up opposites, but not only have I done that, but I've shrunk the numbers considerably. Now if I combine, I get negative x. Negative 2x plus x is negative x. The y's cancel. Negative 550 plus 350 is negative 200. Negative x equals negative 200. Divide both sides by negative 1, and we get x equals 200. But we need to get the y so that we finish the 2 by 2 system. Let's just take x equals 200 and put it right here. Now I could put it back up here, but this is a much easier equation to deal with. 200 plus y is equal to 350, which means that y is equal to 150. Now I just need z. Let's take the original first equation. First equation says x plus y plus z is equal to 400. X is 200. Y is 150. We don't know z. That's equal to 400. 200 plus 150 is 350, plus z is equal to 400. Subtract 350 from both sides, 50. So the answer to the question, we had 200 of the cheaper tickets that were $8 each. We had 150 of the middle price tickets at $10 each, and only 50 tickets that were $12 each. We could check all three original criteria and they should be satisfied. There are a whole lot of other applications that lead to 3x3 systems. Geometry, algebra, engineering, physics, rate problems, money problems, profit and revenue problems, the list goes on and on and on. But they all run the same course. For a 3x3 system, there are 3 things you don't know. You need 3 conditions to set up 3 equations. And once you get the 3x3 system, shrink it down to a 2x2 by picking a pair, eliminate a variable, pick a different pair, eliminate the same variable, solve the 2x2, and then go back and pick up the third variable's value. All right.